does is it excites the electron, and the electron goes to the next electronic energy level, while you lose one light radiation passing through. And if you can find out by checking how many light radiations were striking that and how many are coming out, then you can actually judge and find out how many atoms must be interacting with the light radiation. That is one part of the story. It's quite a rare event. This process is referred to as absorption, when the energy of light gets transmitted to the energy requirement of an atom, and the electron goes to the next electronic energy level. This process is called as absorption. Another possibility is that when the light radiation strikes the electron within an atom, then the energy associated with the light radiation is either more or less than what is the requirement of the electron to undergo the transition. If this is the situation, then there is no energy transaction happening between the light radiation and the electron. And this causes the light radiation to just deviate from its path, and it gets propagated in a different direction now. And there is no change in the energy associated with the light radiation. This phenomena is referred to as scattering of light. Because there is deviation of the light radiation, your detector, which is going to detect the amount of transmitted light after this event, may lose on with this radiation and may record it as absorption. So, to be careful enough in order to study absorption, it is essential that one talks about the light radiation whose energy requirement exactly matches with the energy requirement of the electron. And whenever you are doing such absorption studies, you will have to work up with that monochromatic light radiation or a single wavelength light radiation whose energy matches with the energy requirement of the electron within the atom. So for absorption studies, it becomes mandatory, if you want proper results. That means if you are judging the amount of light absorbed and comparing it with the number of entities present within your sample, then it becomes mandatory that you use a monochromatic or a single wavelength light radiation, and whose energy values are exactly same as the energy requirement of the electron. Is this much fine? Yes, anyone?
Yes, sir.
Okay, good. So now if we are good till this point, then we develop this concept of how different energy light radiations are given out in response to certain events which happen within an atom or a molecule. Now, I gave you this understanding that when we are talking about absorption, the energy is transferred from the light radiation to the electron. And now electron goes to the next electronic energy level. Now, when this electron comes back to its ground state, it is going to radiate out same amount of energy what it has absorbed. And hence, it's a two-way process. The energy, that means according to the law of thermodynamics, energy cannot be created, cannot be destroyed, and it can be only transformed from one form to other, right? So comparing it with this analogy of interaction of light with an atom or molecule, then you need to understand it that it these are the molecular or the atomic events which are going to give rise to light radiations. And when such light radiations interact with other atoms or molecules, then they are going to result into similar kind of events within the molecule or an atom. Give you a clear picture. Okay, to give you a clear picture, this is the slide that can tell you more clearly about what actually is happening. Like the highest energy radiations, we talked about this in the last class, but just I'm giving you a small summary of it. The highest energy radiations are gamma rays. The wavelength is the least, as we know that there is an inverse relationship between energy of light and wavelength. So higher the energy, lower is the wavelength. So when we are talking about gamma rays are the least of the wavelength values, falling in the range of 0.01 nanometers. And the energy is highest, and hence they lead to transitions which are nuclear transitions. We talked about this in slight detail in the last class. So I will not indulge more onto this, just giving you an overview. The second important range is 0.1 nanometer value. And okay, the second important range is the 0.1 nanometer value, which are the X-rays, and these lead to inertial electronic transitions. Other way around, inertial electronic transitions are responsible for giving out X-rays from an atom. Next comes the range in which we are more interested in. This is the UV and visible range. It ends here, this portion. Starts from around 2 nanometer, goes to somewhere around 780 nanometer value. The initial part is called as the vacuum UV, or you can say near UV. And this is the far UV. Far UV region is very close to the visible range. All these radiations following visible, because the last in the visible range is the red region of electromagnetic spectrum. Whatever goes next to red is referred to as infrared. And it can be divided into two halves, the near infrared and the far infrared. So right from vacuum UV to near infrared, this entire region is associated with valential electronic transitions. Energy is variant because it will be different within different atoms, the requirement of electron. It also depends upon where the electron is located when the transition is to happen. And hence, depending upon the type of the atom, these transitions are going to require different amount of energies for transition. Reverse is also true, as I already stated, that valential electronic transitions are responsible for giving out these type of radiations. Next to near infrared is far infrared, which is associated with molecular vibrations and rotations. We'll come to this when we go into understanding infrared spectrometry. There's another form of absorption spectrometry, which is referred to as vibration spectrometry as well. We'll talk about that, how it happens, what happens exactly. And the last in the hierarchy are the least energy radiations, longest of all wavelengths, is in centimeters if you note it. These are microwaves and radio waves. These are associated with oscillations of nuclei and electrons under the effect of magnetic field. So this was where we actually stopped in the last class. This gives you the entire visual of what exactly is associated with all types of light radiations, and what are the energy values and what are the wavelengths in which they fall. We are presently going to look upon to actually only UV visible, and this area is not even vacuum UV, it's actually UV and visible only this range, starting from somewhere around 180 nanometer to going to somewhere around 780 nanometers. Okay. So I hope that this much is fine. Let's move up now into, if you're having any questions right at this moment, then I'm ready to answer. If it's okay, then I can move ahead. Yes, any questions?
No, sir.
Okay, so we will go to the next portion now that perhaps you have already talked about, or you have already uh, so let's go into understanding what are the laws that are given for absorption of light, because they are going to be responsible to give us the concept of absorption. The first ever law that was given, I hope that you have heard about it. It's called as the Buger-Lambert law. It states that the amount of light absorbed by the absorbing material is proportional to the thickness of the absorbing material and is independent of the intensity of incident light. Okay. So in short, what it actually means is this. Now take this example. Okay. Now thickness means the entire path through which the light passes and interacts with the matter, whichever matter that is present inside this particular path length. So the thickness is also referred to as path length, if you might have already heard about it. So the concept goes like that, it's when perhaps there is an absorption of 50% of light, then if the incident light is 100%, when you allow it to pass through something, what comes out is 50%, and so on and so forth. So when you plot this, the understanding goes like this, that when you plot this type of absorption happening in terms of percent transmission. Now this 100% transmission, when the path length or the thickness is 0, then obviously the transmission will be 100%. Now path length 0 means there is nothing that is absorbing. So obviously this is, I hope that you know how to read a graph. So this is the path length plotted against amount of transmitted light, or is in proper jargon is referred to as percent transmission. So if the thickness is 0, then the transmission is 100%. And as you go on increasing the thickness, the transmission drops. And this drop is referred to as an exponential drop. Okay. So to mathematically represent this, it is actually given in these terms. I upon I0 is equal to e raised to minus kb. I'll come to this, but before I go into make you understand that what is actually happening, let me give you a very simple analogy that what exactly I'm actually talking about here. I hope that you have seen gelatin sheets, right, which are available in the market, which are colored and are used for like preparation of those Diwali lamps that you get, right?
Yes, sir.
You have seen those gelatin sheets. So imagine now that in front of you, you have a gelatin sheet which is placed in between a source of light and you, right? There is a single gelatin sheet. Say suppose it is red in color, okay? So whatever that comes to you will be red in color, right? You will see red light coming out. And now imagine that you are seeing it passing through a single gelatin sheet, right? So you will see bright red, right? However, imagine that in place of single gelatin sheet of the red color, I am putting say two gelatin sheets. What will happen? What you will see coming out? So compare it with a single gelatin sheet and you are looking at the light coming out, and two gelatin sheets, and now you are observing the light coming out. What exactly you will observe? What will be the difference?
It will not
Less light
as
will
bright
come.
as.
Yes. So how it will appear if it is red? Will it become dark red? In case you are using two gelatin sheets?
No, sir, it will become light red.
Sorry. Uh, so if it is a single gelatin sheet, it will be bright red, right? And if you
Yes,
use
sir.
two gelatin sheets and now you look at the light coming out, what it will look like? Yes?
Yes, a dark red, but less brighter.
Yeah, obviously. When you say dark, it is because less of the light is coming, right? Are you getting my point? So anything that you say is dark means that there is lesser amount of light, correct? So
Yes, sir.
when you say
Yes,
dark
sir.
red, you are in other words saying that it is less brighter. Now imagine instead of two gelatin sheets, you are putting 3, 4, 5, and 6 gelatin sheets. What will happen to the light that you are seeing on the other side? It will become more and more darker
Yes, sir.
and
Or
less.
might at some point
Yes,
it will
sir.
not appear.
Yes. So it will start to become, can I put it like this? That the amount of transmitted light will be becoming less and less as you are increasing the number of gelatin sheets masking the light source.
Yes,
Yes,
sir.
sir.
Yes. So what exactly is happening is this, right? When you are increasing the thickness of the absorbing material, what the gelatin sheet here stands as an absorbing material. Now to go any further before this, let me give you a perspective of absorption. Now, when anything appears to you in a peculiar color, like say for example, I have written here Booger-Lambert law. What is the color of this? Yes,
Red.
red. Can you tell me why it appears red?
It reflects red.
Sorry, I couldn't hear you properly.
It reflects the red color.
Yes, it reflects red, meaning it is absorbing all other visible colors except red, right? Can I say this?
Yes, sir.
Right. So when we are talking about, say, a gelatin sheet which is red in color, then what happens to the white light which is falling on the gelatin sheet is that all other visible colors are absorbed by the gelatin except red color, right? because it doesn't like red. Maybe it is not liking that red color. So red gets transmitted out. So it is absorbing all other visible colors except red. So there is an absorption happening there. Okay, but instead of putting it in terms of absorption, let us understand first in terms of transmittance, because absorption and transmittance are inversely correlated with each other. So coming back to the same analogy of gelatin sheets, more the number of gelatin sheets placed in between the light source and you, lesser amount of light will get transmitted, or other way around, more amount of light will be absorbed. So putting it in the context of thickness now, as you are increasing the number of gelatin sheet, you are actually increasing the thickness of the absorbing material, right?
Yes, sir.
So as you increase the thickness, lesser amount of light is getting transmitted. So it is now establishing this law perfectly, which says that the amount of light absorbed is directly proportional to the thickness of the absorbing material. So as the thickness increases, the amount of light absorbed will increase, or reverse way around, as the thickness increases, the amount of transmitted light will decrease. Okay, so there is a thickness value plotted over here, which is referred to as path length, and the amount of transmitted light is decreasing. So if I want to represent it in a mathematical term, because there is an exponential decrease, it is represented as e raised to minus because the slope of this curve is negative, is decreasing, right? So it is represented as minus kb. Now k is a proportionality constant, b is thickness value. Is this much fine? So now,
Yes, sir.
what are all these terms are represented over here? I is the intensity of transmitted light. I0 is the intensity of incident light. B is the thickness, and K is the proportionality constant. And because it's a exponential decrease, you have this term as negative. Okay. Now, to make the things slightly more simple for you, is there any doubt till this particular point?
No, sir.
No, sir.
So I hope that we can move ahead.
Yes, sir.
So just remember this equation as we are going to pile up upon this equation. So one law is establishing here. So if I take natural log of both sides. Now, can anybody tell me what do you mean by natural log? Yes. Can anybody tell me what is natural log, or what is log to the base 10?
So natural log is log to the base e.
Correct. So what do you understand when you say log to the base e? Or what do you understand when you say log to the base 10? In simple terms, what it actually means is, let me give you a perspective. Okay. In simple terms, when you talk about log to the base 10, then it means that log of 1 is 0, while log of 10 will be equal to 1. Okay, so whatever is at the base, if you take the log of the same value, then it is equal to 1. In simple terms, if I take natural log, which is written like log to the base e, then log of e would be
1.
1. 1.
yes, obviously, if you correlate it with log to the base 10 of 10 is 1, in the similar value, log to the base e of e would be 1, right? So when you're talking about natural log is also written like this, nothing but log to the base e. If you take log of both sides of the previous relation, that was I upon I0 is equal to e raised to minus kb. If you take natural log of both these sides, then log of e will become 1. And anything that goes in the superscript in the logarithmic consideration comes before the log. So it's nothing but when you are talking about natural log of I upon I0 is equal to minus kb times log of e, that is nothing but 1. So it will be log to the base e I upon I0 is equal to minus kb. This much is fine?
Yes, sir.
Yes, sir.
Or other way
Yes,
around,
sir.
if I don't like this negative sign, right? Because we are biologists and biologists normally are very positive rather than being negative. So it's better that we convert it into positive terms. So natural log of I0 upon I have reversed this now, is equal to kb. Can I write it like this now?
Yes, sir.
Correct. So we have arrived at this relation, which is natural log of I0 upon I is equal to kb. If I take common log or log to the base 10, the natural log can be converted into log to the base 10 by multiplying it with a value of 2.303. Log to the base 10 I0 upon I is equal to kb. This entire term, which is 2.303 log to the base 10 I0 upon I, is referred to as absorbance. Okay, because it's a reverse of transmittance that we actually plotted, right? I is transmitted light, I0 is incident light. If I reverse it, I0 upon I becomes absorption. Okay, so it can be written like absorption is equal to K is the constant we know, B. So I can write it like, in other words, absorption A is directly proportional to B. Fine?
Yes, sir.
That is what the Buger-Lambert law was stating. The amount of transmitted light is, the amount of light absorbed by the absorbing material is directly proportional to the thickness or the path length of the absorbing material. So we have proved it, correct? Now, apart from this, there is another law. It's called as the second law of absorption. Similar to Buger-Lambert law, but it's placed in a slightly different manner. Okay. This law states that the amount of light absorbed by the absorbing material is proportional to the number of absorbing molecules, that is, the concentration of absorbing solution. Now, to give you a perspective, can I not say this, that when the light is traveling through the absorbing material, it is going to be absorbed by the molecules of the absorbing material, right? And more the number of molecules it encounters in its path, more will be the absorption, correct? And how many molecules it encounters in its path, will it not be dependent upon concentration? Like imagine this situation, that the concentration is that there are only just 2 molecules in the path. If I increase the concentration, the number of molecules in the path of the light traveling through the absorbing material can be increased, right? Without increasing
Yes, sir.
the thickness. So what I'm trying to say here is that if I increase the concentration without changing the thickness, then the number of molecules which are interacting with the light radiation that is passing through will be more. And hence, more the concentration, more will be the absorption. Can I say this?
Yes, sir.
Yes, sir.
Right?
Yes, sir.
So that is what is stated here by Beer's law. So can I not, in the similar manner, like I proved it for thickness, that absorption is directly proportional to thickness, can I not say this in the similar manner for concentration as well and get to the same relation? Like for thickness, increase in the thickness was associated with increase in absorption. So we arrived at this relation, absorption directly proportional to thickness. Can I not say this now, that absorption A is also directly proportional to concentration
Yes, sir.
and arrive at this
Yes,
equation,
sir.
correct? So now if A is proportional to B and A is also proportional to C, so can I not say this, that A is proportional to B and C?
Yes, sir.
Yes,
I can
sir.
say this, right? So I can combine the two laws together to get to a combined statement of the law and arrive at this equation. That is, now what I have done here is I have added that 2.303 to, say, okay, I will write it down for you here. Say it was 2.303 log to the base 10 I0 upon I is equal to, now I have combined the two things, so I can write it like K, which is one proportionality constant, K prime, which is another proportionality constant, B, which is small b, and capital C. Can I not write it like this when I combine the two things together?
Yes, sir.
Right? So in the similar fashion, what I can do is that I can take this term here, correct, and arrive at K prime upon 2.303 and make it a common constant, which is written here as A. This is called as absorption coefficient. This is a constant value. So I have combined the things together and have arrived at this equation, that is log to the base 10 I0 upon I is equal to small a, small b, and capital C. Small b is path length, capital C is concentration, small a is referred as the absorption coefficient. Fine. Should I go ahead?
Yes,
Yes,
sir.
sir.
Okay,
Yes,
good.
sir.
So we have arrived at this equation of absorption, and now by combining the two laws together, we arrived at this situation that we can say that the amount of light absorbed by the absorbing material which is referred to as absorbance or extinction, is proportional to the concentration of the absorbing material and to the thickness of the absorbing material. That means both the things, right? I can actually fiddle up with this law and say it like this, that the amount of light absorbed by the absorbing material is directly proportional to concentration, provided I keep the path length constant, right? Reverse is also true. I can say this, that the absorption of light is directly proportional to the thickness of the absorbing material, provided I keep the concentration constant. Okay, both way around I can put it, or I can say it like the combined statement of the law. So now the quantity, that is I0 upon I, is referred to as absorbance, and that is what we note when we do colorimetric analysis as optical density. Reverse of this, I upon I0, is known as transmittance, which we have already talked about. So now we have arrived at this simple relation, capital A is equal to small a, small b, and capital C. Fine up to this point?
Yes, sir.
Yes, sir.
Now, if you say yes, then there are certain things that you need to look upon to here. This absorbance, this concentration, this is absorption coefficient or extinction coefficient, the path length, right? Now, let us find out something quite interesting. We know something about concentration, right? Concentration can be represented in terms of moles per liter or grams per liter. We know something about path length as well. Path length is represented normally in terms of centimeters. Can anybody tell me what are the units of absorbance? Yes?
The nanometer.
Sorry? I couldn't hear you properly.
nm. Nanometer.
Nanometers are the unit for wavelength. It's not the unit for absorption. Absorption is the amount of light absorbed, right?
So we only measure it in the unit of optical density.
Optical density is the unit you want to say?
No, not exactly unit, but whenever we take the absorbance on the colorimeter or whatever, so we write it as like point something of OD.
So, but it cannot have a unit because it's a coefficient.
No, coefficient is different. Small a, I'm not talking about small a, I'm talking about absorbance, capital A. Absorption coefficient has a unit and we'll discuss about that. It's not a rule that coefficient doesn't have a unit. Yes. So we can arrive at the unit of extinction or absorption coefficient only if we know the units of all these values, right? We know the unit for concentration, we know the unit for path length. What are the units of absorbance? Mind you, OD is
Moles per liter into centimeter.
no, that's not the unit for absorbance.
Centimeter inverse.
Centimeter inverse. Why do you say that? Centimeter inverse is a unit of another quantity that is referred to as wave number. That is a different story altogether. We'll come to that when we talk about infrared or vibrational spectrometry. Okay, if the previous slide can help you in some way. Yes. What are the units of absorbance?
AU,
Sorry,
AU,
your voice is not clear. See, absorbance as well as transmittance both are actually the ratios of two same quantities, right? Intensity of,
sir.
yes, right? So if it is a ratio of two same quantities, what is the unit?
Units
No
are
unit,
nullified
sir.
then.
Yes,
Yes, sir.
there is no unit for absorbance. Okay. Now, why this is an important question to be addressed is because we need to find out what are the units of absorption or extinction coefficient. So we need to know what are the units of other quantities, right? Because we don't know what are the units of absorption or extinction coefficient. We know the units for path length, we know the units for concentration. Now we know that absorbance doesn't have any unit. So can you devise the units for absorption or extinction coefficient? Yes.
Liter per centimeter mole.
Liter per centimeter per mole or mole per liter per centimeter?
Liter per centimeter mole.
Liter per centimeter mole. Sure about it?
No, sir.
Liter per mole centimeter.
Are you sure about it? See, consider the unit for absorption are, there is no unit, so I will write it as 1 is equal to A. We don't know the units of small a. What are the units for path length? Centimeters, right?
Yes, sir.
What are the units for concentration? We can either write it as moles per liter or grams per liter, right? So I will take it, say, moles per liter. Now, if I want to solve this equation for A, what should I do? I should take this entire quantity here, correct? So if I take the entire quantity there, then the units for A will be centimeter inverse.
Mole inverse.
right? Liter per mole. Right?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, good. Or can I not write it like this? That it is liter per mole per centimeter. Can I write it like this?
Yes, sir.
Yes, sir.
Right. So when you represent concentration in terms of moles per liter, this value small a is referred to as molar absorption or extinction coefficient. Is written like am, or epsilon is another value which is extinction coefficient. You can write it like epsilon m is referred to as molar absorption or extinction coefficient. And when you represent concentration in terms of grams per liter, then it is written like specific absorption coefficient or extinction coefficient, written like AS. Now the units will be liter per gram per centimeter, right? So now you have two terms with you: absorption coefficient, which is represented as molar absorption coefficient, and the specific absorption coefficient. Can you have a relation established between these two now? Molar absorption coefficient and specific absorption coefficient. Can you establish a relation between the two? So is it possible for me that if I know molar absorption coefficient, then I can calculate the specific absorption coefficient, or reverse way around? Did you get the question?
Yes, sir.
Okay. So what I will do is that I will leave you with this question today, and you will give me the entire derivation for a relation to be established between molar and specific absorption coefficient. Can you do that for me?
Yes, sir.
Yes, sir.
Okay, so we will meet tomorrow again with the explanation for the derivation between molar and specific absorption coefficient. That's homework for you. Okay, if you have understood all of it, then perhaps you would be able to make or devise a derivation between molar and specific absorption coefficient. So in case you are having any questions, you can ask me, or else we will call it a day, and we'll meet tomorrow then. Are there any questions?